Greetings and welcome. In today's video, we're going to be looking at equations of parabolas from the perspective of conic sections. So here's the definition of a parabola, and if you've graphed parabolas using quadratic formulas, quadratic equations rather, in the past, you probably haven't thought of it in this light. But here it says, a parabola is the set of all points in a plane equidistant from a fixed point called the focus and a given line called the directrix. So let's draw an example of what this is describing. So here's my coordinate plane, and so if I have, let's see, I guess I'll draw these in orange, fixed point, and my directrix is my line. Alright, and I want the set of all points that are the same distance from both of these. Well, let's consider the first and most obvious one is the point that's halfway between them in a kind of perpendicular line. But then there's also this one. This point here is the same distance, right? If I can imagine this square. Same distance in both of these directions, right? And not only would there be a point there, but there'd also be a point over here, which is the same distance in both of those directions. But there are more points in between and beyond that. For instance, consider this point here, in which this distance and this distance are equal, right? And as far as the distance to the directrix, it would make sense for that always to be measured perpendicular to that point. And then consider even a point like this, in which this distance and this distance are equal. And let's see, there's that and that. And if I draw all of the points that happen to have that property, what I'm left with is actually a parabola, the same kind of parabola that you've seen before when dealing with, that was a terrible curve, dealing with quadratic equations, right? And so that's what we would end up getting. So this horizontal line is our directrix. Not that it has to be horizontal. Here's our focus. This point is the vertex. We've seen that before. And the distance from the vertex to the focus is p units, and the distance from the vertex to the directrix is also p units. We'll end up using that later on. So here's kind of the basic concept of what's going on. So this is a very different way of perceiving of a parabola than perhaps we're used to. So with this in mind, let's consider the equations of parabolas. I'll have a quick little graph here, and then we'll consider some properties or facts about it. Let's see. Yeah. So the first kind of parabola that I want us to consider is a vertically oriented parabola. Because that is the kind that we're used to. And these kind are actually functions. And now if we think about vertically oriented parabolas in the past, our equation has always been something of the form y equals x squared. And similarly, in this case, our x term will be the one that is squared. So our equation is going to be x minus h all squared equals 4p times y minus k. Alright, so very different than what we've seen in the past. However, in this form, we'll be able to gather some valuable information from it. Similar to slope-intercept form for the equation of a line, that at a quick glance you're able to gather what the slope and y-intercept of that line is and graph it pretty quickly. In this case, we'll also be able to quickly gather some information. So the graph in this case would be something like this, a vertically oriented parabola, right, opening upwards or downwards, depending on the value of p. So the h and k are going to be similar to our other equations of conic sections, in which that'll be a very good starting point for us. But h and k does not represent the center of this parabola. In fact, I'm not sure even what one would mean if they meant center, but it will be our vertex is going to be h comma k. All right, and then the focus. All right, this has a single focal point, and then the single directrix. The focus is going to be p units away from the vertex in the direction that it happens to be oriented. So in this case, if it's vertically oriented, this would be h comma k plus p for the focus. And the directrix is going to be a horizontal line in this case. A horizontal line is always of the form y equals a number. And in this case, it will be p units beneath the k value, so it would be k minus p for the directrix. And then we still can find the axis of symmetry, where that's going to be the line that passes through the vertex and kind of mirrors the parabola over itself. And in this case, that would be a vertical line, x equals h. Let's see. And then regarding the direction that it opens, if p is greater than 0, it opens up. And if p is less than 0, it opens down. All right? So that's our first kind of equation for a vertically oriented parabola, which are the only kind we've seen up to this point. However, since these aren't necessarily functions, actually I don't think any conic section is a function besides a 45-degree rotated hyperbola can technically be a function. But all of the other ones don't pass the vertical line test. And since these aren't functions, we can actually have a sideways parabola. Oh. And it's going to be a sideways parabola anytime our y term happens to be squared. And graphically speaking, if p is positive, it'll open to the right in the positive x direction. And you'd still have your your focus, your directrix, stuff like that. So this is a horizontally oriented. The vertex is the same, but make sure in this case you realize that the x-coordinate of the vertex is always with the x, and the y-coordinate is always with the y, so you don't mix those up. Let's see the focus. In this case, because it's horizontal, it will be p units to the right of the vertex, so it would be h plus p. And actually, if p is a negative value, it'll automatically account for it being in the other direction. So the focus is always going to be h plus p, even if p is a negative number. The directrix will be a vertical line this time, so it's going to be x equals a number, and the number that it equals will be p units to the left of the vertex, so that'll be h minus p. The axis of symmetry is going to be a horizontal line, so that's y equals, and in this case it's going to pass through the y-coordinate of the vertex, so that's just y equals k. And then regarding which way it opens, if p is greater than 0, it opens to the right, and if p is less than 0, it opens to the left. So all sorts of information that can be gathered from the equation in this form. So let's actually consider then a problem and try to put it into this form, okay? So here's an example. So write in standard form, and then we'll even graph it. Graph and give all significant info. And by significant info, I'm referring to the vertex, the focus, the directrix, the axis of symmetry, all of that stuff. So here's our equation. What if I have y squared equals 8x plus 48? So looking at this at first glance, I immediately realize it's not in one of the forms I can work with, but I suspect that I'll be able to put it in this form because I see that the y is the squared term and there's no x that's squared. And unlike all other conics, parabolas will only have a single squared term. So that's one of the ways that it'll give them away immediately. So let's write down some facts we know about this. So I know this is going to be a horizontally oriented parabola. However, I can't gather k or h or p until I kind of deal with this and get it into this form. Now, in this case, I don't have to do any completing the square on the y. I could just rewrite this as y minus 0 all squared. And I notice on the right-hand side, I'm going to want to factor out everything that I can so that I have a positive 1 coefficient for my x. So what would that mean for this problem? So I'm going to want to factor out this coefficient in front of the x. So I'm going to factor out this 8. So I'm going to have 8 times x plus, let's see, 8 goes into 48 6 times, I believe. And now I have it in this form. I technically could also rewrite 8 as 4 times something if I wanted. I actually prefer it in this form right here. So now let's finish gathering our information. So let's see. So our vertex is going to be negative 6, 0. Our focus will be, let's see, it's horizontally oriented. So I'm going to add the p-value to my x-coordinate. So it'll be negative 6 plus p, but I don't know what that is yet. And this is what I'll do. I'll take this coefficient 8 and set it equal to 4p and solve. So if I divide both sides by 4, I end up getting p is equal to 2 in this case. Let's see, I guess I'll box my standard form up here. So I'll add 2 to that, so that's going to give us, I guess I'll use an equal sign, negative 4, 0. My directrix is an equation, not a point, and it's also not just a single number. If it's horizontally oriented, the directrix will be vertical, so it'll be x equals a number. That's just my baby crying. Don't worry about him. My wife's taking care of him. I'm not neglecting my child, that is. So that'll be negative 6 minus the p-value, which is 2. So x equals, I guess actually I shouldn't have all these equal signs here, should I? So x equals negative 8 would be the equation of the directrix. The axis of symmetry will be horizontal, all right? That matches with the that there, so that'll be y equals, and that will be 0 because it happens to pass through the vertex, and the y-coordinate of the vertex would have to match with that equation. So let's see, I think I've got all of the information I need to graph this, so let's do so, and I'm going to hopefully show you some decent strategies for graphing. So let's see, the vertex is at negative 6, 0, and it opens to, actually, oh, I didn't specify which way it opened. Well, let's see, p is positive, so p is greater than 0, meaning it opens to the right. So I guess I have to go as far over as negative 6. And I don't think I'm going to end up going up too high. So let's plot our points. So I've got negative 6, 0 is right here. Actually, I do have to go, sorry, I have to go over as far as negative 8, don't I? Fortunately, I had a little extra room. So here's my vertex. My focus is p units to the right, because it opens to the right. So that's 2 units, so over 2. And negative 4, 0 agrees with that, right? The directrix is 2 units in the other direction, so x equals negative 8. So right like that. And so far, the only point that I've graphed that actually is on my parabola is the vertex. So the directrix and focus aren't on the graph itself. So here, this point exists. And now one of the ways I find a couple other points is the focus is 4 units away from the directrix. So 4 units above needs to be a point, and 4 units below needs to be a point. And let me explain why I know this is true. It's because by the definition, these points have to be equidistant from both the focus and the directrix. So if this is 4, I know that this must be 4, right? So that's one of the ways I can generate a couple other points. And now, typically I would want 5 points to graph a parabola, but since we're pretty familiar with what the shape looks like, I'll just allow the 3 points to be sufficient for that. So here's all of the significant information. Here's the graph, and I can kind of do that little square trick, right? So 4, 4, 4, 4, right? In order to figure out where another point is. And I could technically find others. It is also possible to use my slopes trick from another video to try to get some points on this, but I'm fine with this the way it is. So thank you for watching, and I'll talk to you guys later.